The aim of the actual unit is to show the development of a draining pavement prototype. It would be the solution to one of the problems detected in one chosen school center as a demonstrator platform in this LIFE project. By means of solution based on nature, we seek to improve the habitability and functionality of the outdoor schoolyards, improving also their use conditions. The prototype not only can respond to the detected problem, but its implementation can be extended to other participating centers and to other environment as urban zones to upgrade, squares, urban and semi-urban gardens. For that purpose, we offer different solutions of urban sustainable drainage. We show their advantages and deepen system of pervious pavements. At least, the characteristics of the designed prototype can be seen. The development of the prototype has been made inside LIFE-myBUILDINGisGREEN project. The aim of this project are the promotion, the improvement and the implementation of solutions based in nature for the adaptation of buildings to the climate change. The initial thought of installing the pavement prototype in 3 demonstrator projects could not be finally performed. A flooring company showed interest in producing a small industrial production of the pavement model, on a very small scale compared to what is usually at a commercial level. This meant that the production cost of the material was very high. This cost of the material, added to the transport and the cost of its implementation, exceeded the budgets foreseen in the demonstrator projects for these work units. On the other hand, a platform for testing and evaluating the prototype has been built at the facilities of the Eduardo Torroja Institute of Construction Sciences in Madrid. And wondering what are the advantages that draining urban pavements bring us? On the one hand, we find impervious pavements, asphalt, cement pavements, etc., the most common in our urban environment. This type of paving alters the natural rainwater flow by preventing it seeping into the ground. This generates the accumulation of water on the surface, puddles, and an increase in runoff flows or surface water flows, with the consequent dragging of materials and pollutants to the evacuation system and risk of flooding if its capacity of evacuation is exceeded. On the contrary, permeable urban pavements contribute to restoring the natural flow of water, allowing it to filter into the ground. This prevents the accumulation of large flows on the surface and reduces the volume of water circulating on the surface. In addition, this type of pavement allows the filtering of waste or contaminants carried by the water. Also, in combination with other elements, it allows the accumulation of rainwater for later reuse. In these 2 images we can see some of the aspects discussed above. We now go on to explain the urban sustainable drainage systems, known by their acronym, USDS. Through the implementation of USDS urban sustainable drainage systems, we seek to recover the natural water cycle. To this end, construction elements or systems are used. These ones improve water behavior in the urban environment. Within the water management chain, these types of systems are characterized by allowing the filtration of rainwater, reducing surface runoff. With their use decreases risk of accumulation of water on the pavement surface. Risk of flooding, since we reduce peak flows due to the accumulation of precipitation flows. In addition, the drained water can be accumulated in deposits, for its later reuse. Or it can be filtered into the ground, to recover the natural aquifers. There are many classifications of the types of urban sustainable drainage systems. If we look at the type of measures that are used, we can classify them into those that use infiltration measures, absorbing surface runoff and infiltrating it into the natural terrain. Among these, we can find wells and infiltration ditches or rain gardens, among others. Those that use filtration measures, which retain and filter the particles carried by urban runoff. We can cite, for example, bioretention areas, filter strips and ditches or draining pavements. We also find the measures that are based on the use of vegetation. With the incorporation of vegetation, the aim is to improve the quality of runoff water. We can cite bioretention areas, rain gardens or urban wetlands. The 4th group would frame the detention and retention measures. Here we can mention the large deposits for the storage of rainwater, which can be superficial or underground. Most systems tend to combine measures from these 4 large groups. Next, we will see some examples of urban sustainable drainage systems. The vegetable covers. They act on the precipitation water on the surface of our buildings and are based on a series of layers of accumulation, evacuation, filtering and support of the vegetal cover. In this other image we can see an infiltration ditch. They are used to absorb surface runoff water, infiltrating it into the ground. This reduces the risk of flooding due to the accumulation of peak flows on the surface. In addition, it improves the quality of the water by filtering it. If used in combination with a storage system, they allow the subsequent reuse of water. Another system is retention deposits. As we can see in these images, they can be superficial or underground. Its main function is to retain and accumulate rainwater. With their use, the risk of flooding is reduced, by reducing peak flows, and it is also possible to reuse the accumulated flows. Rain gardens, like the one in these two images, are areas with vegetation that in case of precipitation can flood, thus retaining rainwater. This makes it possible to reduce the risk of flooding, by reducing peak flows. The use of vegetation allows to improve the quality of the water, through its filtering, and helps to regenerate the urban landscape. Another example is draining pavements, already mentioned. This type of pavement retains and absorbs rainwater and improves its quality by filtering the suspended solids carried away. By retaining water, the risk of flooding is decreased. Its use allows rainwater to infiltrate the ground or its accumulation in underground deposits for later reuse. What are, then, the main characteristics of urban draining pavements? First of all, they respond to the functions for which they have been designed, resisting the loads and the wear and tear of intended use, pedestrian, light and heavy vehicle, etc., draining surface water, filtering dragged solids. In addition, other capacities can be added, such as photocatalytic activity. It also brings aesthetics to the city. It can be combined with other materials or it can incorporate vegetation. And since it is an industrially produced material, it is usually modulated and has the possibility of incorporating recycled materials in its production, for example recycled aggregates. We now go on to show the draining pavement model developed within the LIFE project.
When one of the participating schools was visited as a future demonstrator project, it was observed that the outer areas of schoolyard were made of compacted earth. This type of paving has little filtering capacity when it becomes saturated. For this reason, in a climatic zone like that of the participating centers, characterized by regular rainfall and sporadic torrential rains, accumulations of surface water in muddy areas that affect the functionality of these recreational areas occur. To avoid these problems, within the LIFE project proposal, it was proposed to develop a self-supporting, draining pavement that incorporated vegetation, to contribute to the renaturation of the environment. The premises to which the prototype should respond are: pavement for pedestrian traffic, with draining capacity, that it be a self-supporting pavement, that could be installed directly on the ground, on a filtering base or on a concrete slab, that it incorporate native creeping vegetation, and it would also provide photocatalytic properties, which allow the reduction of environmental pollutants, NOx. There are various types of draining pavements on the market. There are concrete, ceramic or plastic models. Each of them responds to one or several of the characteristics sought, but none responds to all of them together. Next, we are going to describe the draining tile developed in the project. The tile is a piece of 250-270 mm of cement mortar. It is composed of two layers. The support layer of compact cement mortar, with its upper face inclined in two planes, for the evacuation of the drained water towards the vegetal channel. The second layer is executed with a draining porous mortar, made of cement and selected gravel. This layer leaves a channel on one side of the tile to arrange the plant substrate and vegetation. To verify the functionality of the tile, the battery of tests included in the standards applicable to this type of tile flooring or cement paving stones and draining flooring have been carried out. The bending resistance, Class 1 ST, has been tested and the breaking load has been obtained, Class 30 marking 3T. With this classification, the tile can be used as paving for pedestrian traffic. Its resistance to wear and tear has been tested, classifying it as Class 2G marking based on the result obtained. This classification makes it suitable for normal use, pedestrian traffic, for example. In the slip test, the result obtained allows it to be classified as Class 3, suitable for use on outdoor pavements as established by the Technical Building Code. The draining capacity of the tile has been tested, obtaining a value for the relative hydraulic conductivity of HC equals 0.042 liters per second. Its draining capacity has also been evaluated by calculating the open porosity. A value of 9.8% has been obtained. To assess the durability of the tile, its resistance to deterioration caused by the action of atmospheric agents, the average water absorption and capillarity absorption have been tested, in accordance with the reference standards. For both parameters, the test values obtained comply with the requirements of the standard. Photocatalytic materials, in combination with a light source that provides energy, allow through chemical reactions to eliminate contaminants from the environment, NOx, and keep the pavement clean. In the demonstrative platform executed, a photocatalytic activator has been applied to half of the installed tiles. The tile prototype developed is completed with the installation, in the drainage channel, of a vegetal substrate and the planting of native creeping vegetation. In this case, Phylla nodiflora has been used. For the prototype, the use of cartridges with the pre-mixed mixture of plant substrate and seeds, bagged in self-composting material, has been foreseen, as can be seen in the upper right photograph. Here we can observe various possible configurations of the pavement, by combining the tile in different positions. Two of the linear configurations have been arranged on the platform, with a single channel or with a double channel. Next, we will show various images of the demonstration platform executed in the facilities of the Eduardo Torroja Institute of Construction Sciences, in Madrid. The first image shows the platform being installed, in June 2021. The second image shows the complete platform and once the photocatalytic material has been applied. In the third image, we can see the installation process of the plant substrate and the specimens of Phylla nodiflora. Due to problems in the supply of the plants, this planting could not be carried out until April 2022. The fourth image shows the state of the platform in June 2022, after a period of drought that caused the loss of the first plantation. In July 2022, a new planting was carried out, as can be seen in the fifth image. The sixth photograph shows us a detail of the sprouting of small specimens in the bagged substrate installed on the platform, in which no new specimens were planted after drying out due to drought. To finish this presentation, we bring the industrial production proposal for the developed prototype. The design of the developed prototype was sent to the company Brainco Smart for its study and estimate of the manufacturing cost. Based on the initial solution of the LIFE project, the company presented its proposal, with slight changes to adapt the prototype to its production processes. For this proposal, with a small initial production for its installation in the 3 demonstration projects foreseen in the LIFE project, the company presented an economic offer that amounted to €110 per square meter. Finally, we collect the bibliography used for the development of this proposal. The images used in this presentation, in addition to those made by the team that has developed the draining tile prototype, have been extracted from the documents and web pages mentioned below.
In collaboration with the LIFE program of the European Union.